In this video, we're going to look at systems of linear equations. So a system of equations just means we have multiple equations. So for example, here we have two equations. One is 4x minus 7y equals 23, and the other is y equals 3x plus 4. Both of these two equations happen to be linear equations in two variables, that is x and y. A solution to a system of linear equations is an ordered pair or a point which satisfies all of the equations in that system. So for example, our system of equations has a solution of -3, -5. And I can check that by plugging in the point -3, -5 into each equation and seeing that it's true. In fact, I've already done that. Once we look at 4x minus 7y equals 23, if I plug in -3 for x and -3 for y, I end up with the equation 23 is equal to 23. If I'm looking at y equals 3x plus 4, again, plugging in -3 for x and -5 for y gives me -5 is equal to -5. So this is a true statement, and this is a true statement. Therefore, this point is a solution for both equations in this system. As we said just a moment ago, since both of these equations have -3, -5 as a solution, then -3, -5 is a solution for the system of equations. Now, we can, if we're given two equations and two variables, if we have linear equations, then we can graph each linear equation, the graph of which will be a line. A solution makes both equations true. Therefore, it's a point which is in common to both lines. So if we have two equations and two variables, we have two lines. And the solution to a system of linear equations is the point at which those two lines cross. Now, technically, we can have as many variables and as many equations as we want in the system. If we have two variables and two linear equations, then most of the time, these two lines cross. But on occasion, these two lines may end up being parallel. In that case, there'd be no solution. So most of the times, our lines cross, and we end up with one single solution, which is the point where those two lines intersect. Also, we can have two parallel lines, which is going to put us into a situation where our lines never cross, so there's no solution. Lastly, we may get two lines that are actually the exact same line graphically, and that will lead to infinitely many solutions. So let's take a look at that graphically. Graphically, most times when we have two linear equations in two variables, we get a single point like we had in our case. But on occasion, we might end up with a scenario in which the lines are parallel and then they never cross. Or we might end up where the two lines are actually right on top of each other, and then every point on this line is a solution. Now, this is the scenario for when we have two equations and two variables. However, the same holds true when we have three equations and three variables, or four equations and two variables, or two equations and four variables. We're always going to either get one solution, no solutions, or infinitely many solutions to the system of linear equations. So the idea here is going to be finding that solution or finding solutions to the system. There's many techniques that we can utilize. One is graphing. When you're doing graphing, it works in certain cases. It doesn't work quite as well in others. There's also a technique called elimination or addition. Some people will call it the elimination technique, others will call it the addition technique. And then there's another technique called the substitution technique. We'll look at all three of these techniques for solving the system. Let's take a look at this example. It says solve the system via graphing. We have 2x minus y equals 5, and 3x minus 4y is equal to 10. There's a couple of different ways to graph. We can graph by hand. Usually if I graph by hand, I like to write out these equations in slope-intercept form. So what I would do for the 2x minus y equals 5, I would rewrite that by subtracting 2x from both sides and then dividing by -1. For the 3x minus 4 equals 10, minus 4y equals 10, I would do the same thing. I would subtract 3x from both sides and then divide by a -4. I'd get y equals 3/4 times x plus 2.5 or 5 halves. It doesn't matter how you write that, or excuse me, minus 2.5 or 5 halves. And then I would graph these two. Normally what I would do is I'd use like the TI-84 calculator to plug those two equations in, and then use the features of the TI-84 calculator to see where those lines intersect. You can also use Desmos if you have access to that. And Desmos, you can plug in this original equation version, or you can plug in the slope-intercept form version. Either way is fine. Let's go ahead and do that. Now, if you were doing this by hand, on that first line, we would have saw that the line goes through the point 0, -5, and then the slope was a +2, so you'd go up 2 over 1, up 2 over 1, up 2 over 1, and you'd keep graphing it like that. And you get this blue line. That's the same thing as the line 2x minus y equals 5. On the other one, we saw that it went through the point 0, comma, -2.5, and then it was a slope of 3/4. So up 3, over 4, or you could think of that as up 1.5 over 2. In either case, we can visually see that these two lines intersect at the point 2, -1. So that's the solution to this system of two linear equations. It's the point 2, -1. So whether you write the equations like the original or you write the equations in slope-intercept form, we get the solution of 2, -1. And that's it. So graphing, you either use a graphing calculator, you can graph by hand if you'd like, but we're just looking for where those two lines intersect. Now there's a couple of features that are tough to deal with if you're graphing, and those features are especially tough if you're graphing by hand. We end up with problems when the X and Y values aren't nice whole numbers, when they're ugly decimals. We also might end up with problems if the point is something that's way off the graph that I don't see immediately. So we end up turning to some other methods. The first algebraic method that we're going to look at is the addition method or the elimination method. Some books call this the elimination method. Some books call this the addition method. And basically what we're going to do is we're going to align all the terms in the equations. So align terms in one equation with the other. And then we force opposite coefficients on one of the variables. Once we do that, we can add the two equations together, which will eliminate a variable. Then we solve for the variable that remains, and then we can plug that back in and solve for the eliminated variable. So the goal is to go from two equations with two variables down to one equation and one variable. Let's do an example. Let's say we have this system of two linear equations with two variables. 5x minus 4y is equal to -1, and 2x plus 7y is equal to 34. Let's go ahead and solve this using the elimination or the addition method. This system is already kind of set up nicely for us because we have the x's aligned, the y's aligned, the equal signs aligned, and the constants aligned in the two equations. So we treat this, well, not just we treat, but this is already lined up. Now I decide whether I want to eliminate the x or eliminate the y. You can do either, but I'll eliminate the y variable. So what I do is I look at this first equation and I'll write parentheses around it. Then I'll write parentheses around the second equation. Now in the first equation, the variable y has a coefficient of -4. In the second equation, the variable y has a coefficient of 7. So what I'll do is I'll start by putting those coefficients in front of the other equation. So I put the 7 in front of equation 1 and the -4 in front of equation 2. And then I switch one of the signs. I'll switch the -4 to a +4. And then I'll multiply by those coefficients. So multiply each term in the equation. It would give me 75x minus 28y is equal to -7. Don't forget to multiply the constant by the -7 as well. And then in the second equation, I get 8x plus 28y is equal to 4 times 34. That's 136. And now, by doing that, I've forced opposite coefficients on the y variables. One of them has coefficient of -28. The other has coefficient of +28. And now, essentially, what I do is I add the two equations together. So when I add the two equations together, 35x plus 8x becomes 43x. -28y and +28y cancel each other out and give me a 0. And then on the right-hand side, I get 129. 136 minus 7 is 129. Now I have one variable remaining. X is my remaining variable. And I can solve for x by dividing both sides by 43. When I do that, I get x is equal to 3. And now, lastly, since I know x is 3, I can find the corresponding y by plugging it in into either this first equation or this second equation. Either way is fine. You just got to plug in. Into one of the equations. I think what I'll do is I'll use the second equation, but I could have just as easily used the first equation. So the second equation is 2x plus 7y is equal to 34. Now we know that x has to be 3. Replace that x with a 3, and that gives me 6 plus 7y is equal to 34. Subtract 6 from both sides, and that would give me 7y is equal to 28. And that gives me y value of 4. So once I've done the elimination, got the x value, I plug it in to my second equation and get the corresponding y value. In this case, we saw that the solution is the 0.3, 4. Now that's pretty nice numbers to deal with. 3 and 4 are both whole numbers. But you could imagine if you got some ugly decimal or some ugly looking fraction, that this method could give you a slight advantage over graphing. So there you go. That's how we do solving the system with two equations and two variables. using the elimination or the addition method. The key feature is this process that if we wanted to eliminate y, we put the variable outside the other equation and then we change one of the signs. If I had wanted to eliminate the x, I would have put a 5 in front of the second equation, a 2 in front of the first equation, and then I would have negated one of them. I'd have changed the sign from a positive to a negative on one of them. So there we go. By the way, a good way to check your solution is to plug that point in to both equations. If you plug in 3, 4 into this first equation, you'll get a true statement. If you plug in 3, 4 into the second equation, you'll also get a true statement. So in this situation, we did see that the solution was correct. Let's try another example where we solve a system using the elimination/addition method. Go ahead and push pause on the video if you'd like to do this on your own. In a couple of seconds, I will show you how it's done. So here's the situation. We have these two linear equations, and we want to eliminate one of the variables. Doesn't matter which one, but since we eliminated the y in our previous example, I'll eliminate the x in this example. So I'm going to put a 3 out in front of the first equation because that's the coefficient of x in the second equation. And I'll put a 2 in front of the second equation because that's the coefficient of x in the first equation. Now I'm going to negate one of those. I could put the negative on the 3, or I could put the negative on the 2. I'll choose to put the negative on the 2. And then we multiply. So multiply out. I end up with 6x plus 3y is equal to 24. That's what you get when you multiply all three terms of the first equation by 3. When you multiply the three terms of the second equation by a -2, you would end up with negative 6x plus 6y is equal to 8. And now we can simply underline, or excuse me, add those two up. I'm going to underline that. And when we add those two equations up, what we'll see is that the x's cancel out. I'll end up with 9y is equal to, it looks like 32. So y is equal to 32 over 9. That is not a super nice number, about 3.5 repeating. But that's perfectly okay. Now, if you want to, you can plug this number into your first equation and then solve for x, or you could plug that number into your second equation and solve for x. Instead of doing that, maybe I don't like to deal with ugly looking fractions. So maybe I could do the same process, but eliminate the other variable. Instead of eliminating the x variable, I could do that same process over and eliminate the y variable. Let's try that. So if I'm going to eliminate the y variable, I look at the coefficients on the y. And I would take the -3. I'd write it in front of the first equation. I'd take the +1, write it in front of the second equation, and then one of them has to change signs. I'll change the -3 to a +3 and then multiply. When I do that, I get 6x plus 3y is equal to 24. And then I end up getting 3x minus 3y is equal to a -4. Now, if I add these two equations together, what I'm going to get is 9x is equal to 20. Dividing both sides by 9 gives me x is equal to 20/9. So this tells me that my solution is going to be the point 20/9 as the x value, and then 32/9 as the y value. That would be a hard point to recognize on a graph if you did it by hand. And even with intersections, you might not be able to identify the decimal points there. Even using technology to find intersections, you might not find the decimal version of that very well. Now, if you ever want to try and see if we got the right answer, plug in the x and the y into both equations. Into the first equation, 2 times 20/9 plus 32/9, and confirm that gets you out an 8. And then take 3 times 20/9 minus 3 times 32/9, and see that that gives you a -4. It turns out in both cases that works. So this is the correct solution to that system of linear equations. So there you go. Now we've seen the solution via the elimination and the addition method. In example 2, it turned out with really nice whole numbers. In example 3, we had rational numbers that were kind of ugly fractions. So what we're going to do now is look at another method. This is also going to be an algebraic method, but we're going to use it in another circumstance. Primarily, the substitution method is used when one of our equations looks like a variable equal to an expression. So if one of our equation looks like y equals mx plus b, then we have the substitution method. And what I do is I substitute this expression for the variable in the other equation. If I do that, I'll get just one variable in the equation and then solve for that variable. After that, I can solve for the eliminated variable by either plugging in the number or doing another substitution method. Again, in this substitution method, when we do this, we're going to eliminate one equation and one variable, and then solve for that remaining variable. Let's do an example. Here we have y is equal to negative x plus 8, and 2x minus 2y is equal to 6. That's the system of linear equations I'm looking at. So this one is set up nicely for substitution. And what I'm going to do is I'm going to plug in the negative x plus 8 into the variable y for our, I should say, in, how do I say that? Plug in negative x plus 8 into the variable y in the second equation. So what that does is it takes this expression, since I know that expression is equal to y, I plug it in for the y in that second equation. So I'm going to get 2x minus 2 times the quantity negative x plus 8. So 2x minus 2. Be careful when you plug that in. You need to plug it in inside of parentheses. And then set that equal to 6 because the right-hand side is equal to 6. That's the substitution part. Now, this equation only has one variable. So what I can do is I can do the distributive property. Again, be very careful of how you do that. Negative 2 times negative x gives me a positive 2x. Negative 2 times 8 gives me a minus 16. And then I'm going to do two steps at once. I'll take 2x plus 2x and get a 4x, and then I'll add 16 to both sides. If I take 6 plus 16, I get a 22. And now I can divide by 4. So that means x is equal to 5.5. Once I know that, I plug in 5.5 for my x. I'll do it in the first equation because that one's going to be easier to deal with. So I go y is equal to negative x plus 8, and then I replace this x with a 5.5. If I do that, I get a y value of 2.5. Now, this tells me that the solution to this system of linear equations is the point 2.5, comma, oh, I'm sorry, I got the wrong one in front. You always do alphabetically, so x comes first. X is 5.5, and then y, which is 2.5. So x comma y, 5.5 comma 2.5. And if you want to check that solution, you can always plug it back into both equations. So 2 times 5.5 minus 2 times 2.5 should give me a 6. And then negative 5.5 plus 8 should give me a 2.5. So that's the solution to this system of linear equations. And again, this system was set up to do substitution because I already had y equals an expression in x. Take a look at example 5. If you want, push pause on the video and try that one on your own. In a couple of seconds, I'll show you how this is done. In this case, what we have is our second equation is solved for a variable. We already have x is equal to an expression in our second equation. So what we would do is we would plug in this 3y plus 2 for the x value in the first equation. Again, that's because we have x equals an expression in y. So I'd take 2x minus 6y equals 4, and I would replace that x or substitute that x out for 3y plus 2. Now what's going to happen is I'm going to solve for y. Distribute the 2, I would get 6y plus 4, then minus 6y is set equal to 4. Now something really strange happens here because both the 6y and the minus 6y are on the same side of the equation. When I add those two up, I will eliminate the variable y as well. And I end up with just 4 equals 4. This is a true statement. And so what that means is that there are infinitely many solutions. In other words, this true statement means that no matter what value of y you plug in, it will give you a true statement. And no matter what value of y you plug in here, you could plug in something there, get an x value, plug in something here, solve it, you get the exact same x value. In other words, these are actually the same line. So in the process of eliminating one variable, I've accidentally eliminated both. When that happens and I have a true statement, I end up with infinitely many solutions. Now, if I would have ended up with a false statement, something like 4 equals 14, then I would have ended up with no solutions. That's the no solution case. But if I end up with a true statement, I end up with infinitely many solutions. By the way, I'll quickly graph both of these lines and show you that they are right on top of each other. So I've graphed both of these lines, and you can see that if I highlight each of them, it highlights the actual same line. So every point on this line, every point on each is shared, and so there's infinitely many points where those two lines intersect. Therefore, there's infinitely many solutions to this system of linear equations. So again, that system we saw by substitution had infinitely many solutions. And that is the scenario in lots of other situations as well. We could have ended up doing an elimination method that gave us infinitely many solutions. Both the x and y would have dropped out. Or doing an elimination method, which would have given me no solutions. And again, the x and y would have dropped out. Now that we've seen these scenarios, we can use these techniques in order to solve word problems. In particular, in this class, we'll look at some mixture problems and some problems involving multiple percentages. So here's a classic mixture problem. Let's say we have two acid mixtures that are to be added together. One consists of a 14% acid and the other consists of a 45% acid. We want to add these two together and make 210 milliliters of something that has 22% acid. It turns out this can be set up using two linear equations. I'll show you how that's done. So we want to add two up. And let's start out by just saying A, we're going to call the amount of the 14% acid mixture. And we'll call B, I'll use a capital B there. I'll call that the amount of the 22%, excuse me, the 45% mixture. Those are the two amounts I don't know. But here's what I do know. I know that those two amounts are going to be added together, and then they're going to make 212 milliliters of a 22% acid mixture. We're going to set up two equations. One is going to be the total amount equation. That is going to say A plus B has to be equal to 210. When we add the A with the B, they have to add together to be 210. So that's sort of my total equation. The second equation is what I'm going to call the acid amount equation. The amount of acid in A is 14%. So the amount in A is going to be 0.14 times A. The amount of acid in B is going to be 45% of B. And lastly, the amount of acid in my final mixture is going to be 22% of this 210 number. This gives me two linear equations that I can use either elimination or substitution on. I'm going to use elimination. I'll eliminate the variable b. And when I do that, I take the exact same approach that I've done before. I set up my two equations. Now, before we do anything else, let's take 22% of 210 milliliters. That's 46.2 milliliters. So while it's 210 milliliters total, 46.2 of that is going to be acid. And then just like before, using elimination, I'm going to put parentheses around each equation. I'm going to write the coefficient of B in the first equation in front of the second equation, the coefficient of B in the second equation in front of the first equation, and then I'll make sure one of them is a negative. I should say I'll negate one of them. I'll change the sign on one of them. In this case, that happens to force one of them to be a negative. Now let's multiply through. I'm going to end up with negative 0.45a minus 0.45b is equal to negative, well, 210 times 0.45 is going to give me negative 94.5. In the second equation, I don't have to do much because 1 times anything is itself. So I still get 0.14a plus 0.45b is equal to 46.2. Add these two together. When I take negative 0.45 and add 0.14, I get a negative 0.31. So negative 0.31a. Negative 0.45b plus positive 0.45b gives me 0. And then negative 94.5 plus a positive 46.2 gives me a negative 48.3. Dividing both sides by negative 0.31 gives me A is 155.81. Oh, excuse me. I'm going to write that out as a fraction. When I ask my calculator to give me that as a fraction, it gives me 4830 divided by 31, which is approximately 155.81 rounded to 2 decimal places. Now, then I just plug that in into, let's say, the first equation. If I plug that into the first equation, A plus B equals 210. A, now we know, is this 4830 divided by 31. And so all you'd have to do is subtract that number from both sides of the equation. If I do that, I get 1680 over 31 as my value of B. Which is about 54.19. Again, you can check that these two numbers add up to 210. Looks like these two numbers add up to 210. And then if I plug those into this equation, the second equation, they should also work. So 0.14 times 155.81 plus 0.45 times 54.19. Add those together and you get right about 46.2. So I've got the right answer here. If I were to write the answer out, I would say that since A stood for the amount of 14% and B stood for the amount of 45%, I would say mix 155.81 milliliters of the 14% with 54.19 milliliters of the 45%. And there you go. That's the solution. Obviously, if you're trying to guess and check at the answer, it'd be really hard to come up with those numbers as the answer. because those are really tough numbers to come up with just by guessing and checking values for A and B. But using a system of linear equations, and in this case using the elimination method, works just fine. Here's another example that you can try. If you want, push pause on the video, read this problem, and then try it on your own. In a couple of seconds, I will show you how it's done. Now, the key thing here in this problem is to look at this and take one of two paths. So basically, the mixtures are different mixtures of strawberry and blueberry. So we'll call mixture A the amount of the 72% strawberry. And obviously by default, the 28% blueberry. And then we'll call mixture B the amount of the 50% strawberry. Once I do that, then I'm all set up. And obviously 50% strawberry by default has 50% blueberry pieces. Now, if I just think about it in terms of strawberries, I can set up two equations. I can set up one that is the total amount equation. A plus B, the two mixtures, have to add to make a 30-pound mix. And then my second equation can be the strawberry mixture ratio. That is 72% of mixture A is strawberries, 50% of mixture B is strawberries, and that better give me out 60% strawberries in the final make of 30 pounds. So I get 60% of the 30-pound mix. Now you may say, what about the blueberries? Well, it turns out if you did a blueberry percentage, it would just be the reverse. So it'd be 28% of A plus 50% of B is equal to 40% of the 30. And it turns out that these two give you the exact same information. In fact, if you take this equation and then you subtract this equation, you get exactly this third equation. So really, you only need either a strawberry equation or a blueberry equation to be able to solve this, but you don't need to use both. That's the trick in this case. So now let's eliminate the variable B in this case. You could eliminate A as well. But if I choose to eliminate variable B, I'll do it just like we did the previous problem. I would put 0.50 in front of the first equation. Put a 1 in front of this second equation. By the way, 0.6 times 30, I'm just going to go ahead and multiply that, and that gives me 18. And then I'll change the sign on one of them. I can either change the 1 to a -1, or I can change the 0.5 to a -0.5. That's what I'm going to do. Now we can multiply. multiply through, that gives me negative 0.50 times A minus 0.50 times B is equal to a negative 15. And then when I multiply 1, nothing changes. 0.72A plus 0.50B is equal to 18. Adding the two equations together gives me 0.22 times A is equal to 3. Now, if I take 3 and divide it by 0.22, I get kind of an ugly decimal, but that's all right. Fraction-wise, that means that the A is 150 over 11, which is approximately 13.64. And then I'd plug that in into the first equation. That way I can solve for B. First equation was just A plus B equals 30. Plugging in that value of A. So I plug in 150 over 11 in for the A, add B to that and get a 30. Then I'd subtract that number. So subtract 30 minus 150 over 11. And we would get, let me do it the fraction first. That's 180 over 11. So the B value is 180 over 11, which is approximately 16.36. And there you go. So as far as the mixture goes, mix 13.34 pounds, 13.64 pounds of the 72% strawberry and 16.36 pounds of the 50% strawberry. And that'll give you the correct amounts that you want. You can always check that by plugging it into both equations and seeing that those answers give you the correct answer. So there you go. Now, in both of these cases that I've done, we've come out to some pretty ugly numbers that are not whole numbers. And that's by design. They're not always going to come out to nice whole numbers every time we try to get an answer. And that's one of the nice things about having these algebraic techniques of elimination and substitution. When we don't get nice answers, we can still get answers. If I were to graph a couple of these two equations, I might not be able to see exactly where they meet up, especially if I did that by hand. So that's how we can do these mixture problems with percentages. Let's do one more example. Let's say at the beginning of a year, an investor puts in 12,600 into stocks. And then he doesn't know exactly what's going to happen. But after a year, stock A earns 5.6% interest and stock B earned 7.1%. If the investor made a total of $776.10, how much was put into each stock initially. This is very similar to what we've done. So you can push pause on the video and try this on your own if you'd like. Otherwise, in a couple of seconds, I will show you how it's done. In this scenario, we have stock A and stock B, so the variables are going to be A and B. You could use whatever variables you want. But initially, the amount that he puts in or she puts in is 12,600. So it doesn't say if it's he or she, but the person puts in 12,600. That means the amount they put in A and the amount they put in B added together to be 12,600. Now, that's our first equation, how much was put in. The second equation is going to be how much was made. The investor made 5.6% on stock A. So whatever they put into stock A, if I multiply that by 0.056, that's the decimal version of 5.6%, I'll get how much they made on stock A. And on stock B, they made 7.1%. So the total amount that they made on stock B is going to be 0.071 times B. It says in this case, the dollar amount that the investor made. The investor made $776.10. Notice it didn't say the investor made 6.2% total. If it said 6.2% total, then we take 6.2% times 12,600. But it just said that the investor made $776.10 total. So now let's eliminate a variable. I've eliminated B the previous two times, so might as well keep up the trend. We'll eliminate the variable B. I'm going to put in a negative 0.071 in front of the first equation. And then I'm going to plug in a 1 in front of the second equation. That's because the coefficient of B in our first equation was a 1, and the coefficient of B in our second equation was a 0.071. So I have to negate one of those, change the sign on one of those, and then I can multiply. If I do multiply, that first equation becomes negative 0.071a minus 0.071b is equal to negative 0.071 times 12,600. That becomes a negative 894.6. 1 times anything is itself, so the second equation is still 0.056a plus 0.071b is equal to positive 776.1. Now I can add things together. So if I add things together, let me put a line there. So we're going to get a negative 0.015 times A is equal to 118.5. Dividing by negative 0.015 5 gives an A value of 7,900. This was a nice whole number. Always nice when I get whole numbers to deal with. And then I plug that in. I'll do that to my first equation. So A plus B equals 12,600 now becomes 7,900 plus B equals 12,600. Subtract 7,900 from both sides, and you get that the value of B should be 4,700. Now, this was all in monetary amounts. So this means that the investor put in 7,900 into stock A and 4,700 into stock B. You can check that that makes sense by adding those two up and seeing that you get 12,600. And then you can also check by plugging those into the second equation and seeing that you get a true statement. It turns out you do in both of those. So that's the final answer for this word problem. Now, all of these word problems dealt with percentages, but solving linear equations can look like a lot of things. There's a lot of different word problems that you could come up with, which forces you to solve a system of linear equations. I won't go through all of them. I'll just say that more exist that we haven't gone over, but the principles are still the same. Now, the last thing that we're going to cover in this video is the 3 variables and 3 equations system of linear equations. So let's say we have a system of linear equations with 3 variables and 3 equations. What are we going to do? Well, in short, we're going to pare that down to 2 variables and 2 equations, and I know how to solve 2 variables and 2 equations. And so you ask, well, how do I get from 3 variables, 3 equations to 2 variables and 2 equations? And essentially what I do is I pick 2 pairs of equations, and I'm going to eliminate the same variable in each pair. Once I eliminate the same variable in each pair, then I've got 2 variables left, and I have a pair of equations, so I'll have 2 equations left. So I'll have 2 equations and 2 variables, and then I can solve that system of 2 equations and 2 variables. Once I have the 2 remaining variables, then I can plug those in and find the last variable. And again, goal is to eliminate 1 equation and 1 variable. So let's do an example where we can do that. Here we have a system of 3 equations and 3 variables. Our variables are x, y, and z. Now, I've situated these equations in such a way so that they're all lined up. The x's are lined up, the y's are lined up, the z's are lined up. The equal signs are lined up, and the constants are lined up. So I want to pick a variable to eliminate. In this case, you can actually use either x, y, or z. So I'm going to try to eliminate z. Let me show you how this is done. All right, So I want to eliminate the z. And so I'm going to take two pairs of equations. I'll take the first two equations. That'll be one pair. And then I'll take the second two equations. I can't take the first two and the first two again. I can take the first two and then the second two, or um, I can take like equation 1 and 3 if it's more helpful as well. Now, then I'm going to eliminate the z on each of them. So what I would do, we're going to decide to eliminate the variable z. In this case, that's already really nice because those two equations, let me just copy these, already are such that when I add them together, I eliminate the z. In other words, I already have opposite coefficients on my z. So when I add those two together, I get 2x plus 2y is equal to 16. On the second pair, let me give a little bit of space there. It's always weird when I'm dealing with this columns wise. So on the second pair, to eliminate the z, I'm going to multiply the first equation by a 2. Notice that when I multiply, that ends up getting me 2x plus 8y minus 2z is equal to 20. Excuse me, I put the parentheses around just the left-hand side. It needs to be around the entire equation. And then the second equation, I would multiply by 1. That's not multiplying by anything. So I would get 2x minus 6y plus 2z is equal to 6. And now I'm ready to add. So I'm ready to add those two together. That gives me 4x plus 2y is equal to 26. So I started with these two, and these two as separate pairs of equations. I eliminated z on one of them and then eliminated z on the other one. And now I have two equations just involving x and y. So now I can bring those back together. We have one equation that says 2x plus 2y is equal to 16, and another equation which says 4x plus 2y is equal to 26. And I solve these like I would any other system of two equations and two variables. Things are lined up, so let's go ahead and eliminate the y variable. I would multiply the top one. You could multiply by 2 and -2, but it's actually quicker just to multiply by -1 on the top. That would give me -2x minus 2y is equal to -16. And multiply by 1 on the bottom would give me 4x plus 2y is equal to 26. Add those two together, and we end up with 2x is equal to 10. Now we're all set. Now divide by 2, I get x equal to 5. Once I know the x value, I can plug that back in into either of those. I'll plug it into 4x plus 2y equals 26. So plug into. You could also plug it into 2x plus 2y equals 16. But we get 4 times 5 plus 2 times y is equal to 26. 4 times 5 is 20. If I subtract 20 from both sides, I get 2y is equal to 6. So y is equal to 3. Now I know the x value. Now I know the y value. And so I'm going to plug those into one of the first equations. Doesn't matter which one we use. We have an x, a y, and a z. So if I use this first equation, the second equation, or the third equation, I should get the same thing. I'll use that very first equation. So plug those into that. Let's eliminate that. The x was 5. The y was 3. When I combine like terms, I get -1 plus z is equal to 6. So that means that z is equal to 7. So now I have my solution. My solution is happening when x is equal to 5, when y is equaling 3, and when z is equaling 7. So there you go. By the way, sometimes we would write that as an ordered triple instead of an ordered pair. And if you're writing this as an ordered triple, just like when you write things as ordered pairs, you write them in alphabetical order. So the x, then the y, then the z. So usually that's how it works. 5, 3, 7 if we had to write it as an ordered triple. But the whole thing hinges on taking two pairs of equations and eliminating the variable z on both of them. That brings us to two equations with two variables, and then we can go from there. Let's try one more example of a system of three equations with three variables. Here, not every variable is present in every equation. If you want to try this on your own, push pause on the video, try this on your own. In a couple of seconds, I'll show you how it's done. Now with this system, it might be a little bit tricky at first before you see the trick, I guess. But we're going to take two pairs of equations and eliminate the z value. So we're going to eliminate the z variable on both, okay? Now my first equation is just x plus 3y equals 2. If I want, I can just take that x plus 3y equals 2 and use it as one of my final equations in my system of two linear equations with two variables. Again, since z is already eliminated there. You could also think of this as eliminating the z using the same trick as we always do. So let's say I took the first pair of equations and I made that my first pair. And then I took my second pair of equations and I'll make that my second pair. It's always happening. Now, if I try to eliminate z here, I would have to put the coefficient of z in front of this first equation. That's a -4. And then I take the coefficient of z of this equation and put it in front of that equation. But the coefficient of z in the first equation is 0. So that would just get rid of that second equation. And all I would be left with is -4 times the first equation, which is algebraically equivalent to the first equation anyways. I could divide both sides by -4 and get that. Technically, I'd have to change the sign on one of those, so change that to a +4. Now, in a similar way, if I'm going to eliminate z from the second pair, I take the first equation in front of it. I'll put out -3. In front of the second equation, I'll put out a -4, and then I'll change the sign on one of them. I'll change the -4 to a +4. This gives me -6x plus 12z is equal to 0. 0 times -3 is 0. And then I get 4x plus 4y minus 12z is equal to -24. Add both of these equations together. The z's cancel out. 4x minus 6x becomes -2x. The 4y doesn't have anything to combine, and that's set equal to -24. So that's what we end up with as our two equations. Now, usually I don't do this process here on the first pair. I just state that, well, since the first equation doesn't have a y value, we'll just use that first equation as one of them and then eliminate the z value in this second pair. So that's typically what we do. Now I have two equations and two variables, and I know how to deal with that. What I'll do is I will take those and I think, let me do this. Let me eliminate the x. I think that'll be less multiplication. So put a -2 in front of the first equation, put a +1 in front of the second equation, and then change the sign on one of them. I'll change the -2 to a +2. When I multiply, that's going to give me 2x plus 6y equals 4, and then -2x plus 4y is equal to negative 24. Now I can add those two equations together. That gives me 10y is equal to negative 20, which tells me y has to be negative 2. If y is negative 2, I'll plug that back in. In this case, I'll plug it into x plus 3y equals 2. That'll say x plus 3 times negative 2 is equal to 2. That's x minus 6 is equal to 2. If I add 6 to both sides, I get an x value of 8. Once I have those two, then I can plug it into any of my first equations that involve a z in order to find the z. So I can either plug it into the second equation or the third equation. Plugging the x and y into this first equation don't help me. I'll take the simpler of the two. So I'll plug into 2x minus 4z equals 0. That means 2 times 8 minus 4 times z is equal to 0. So if I add 4z to both sides, I get 16 is equal to 4z. Dividing by 4 tells me that z has to be equal to 4. So my solution happens when x is equal to 8, y is equal to negative 2, and z is equal to 4. As an ordered triple, that would be 8, negative 2, 4. Again, x, y, z in that order. If you wanted to test this out, you could go back to your original problem and plug in 8, negative 2 to the first equation, plug in 8 and 4 into the second equation, and then 8, negative 2, and 4 into the third equation. It turns out that if you do that, you'll get a true statement in every equation. So 8, negative 2, 4 is the unique solution to this system of 3 equations with 3 variables. Now, again, I'll emphasize even in the 3 equations, 3 variables case, my options for solutions is that I get a single solution, which is an ordered triple, or I get a no solution problem, or I get infinitely many solutions. So that is the same option in in systems with 3 equations and 3 variables, just like it is with 2 equations and 2 variables. And in fact, if the system had 5 equations and 4 variables, the same thing would be true. We'd have those same options. So there we go. That is how we can deal with systems of linear equations. Obviously, there was a lot in this video, and in every single thing, you could dive down into some details. We obviously used elimination a lot. We could have used substitution as well in the word problems and in the systems of 3 equations and 3 variables. But we just used the easiest way that I thought possible. So there you go. That concludes this lecture on systems of linear equations.